This is the last section of the matrices chapter, and it's all about solving simultaneous equations and solving systems of equations using matrices. Now, it's not too difficult to solve an equation, maybe something like this. Yeah, I'm making this up, so I don't know whether it has solutions or not. It may do, it may not do. Okay, that's quite easy. We've got methods we can solve simultaneously by substitution. So you take one of the equations, make x or y the subject, substitute into the other. Elimination, which means basically multiplying one of both of the equations, then add or subtract to get rid of a variable. Or we could even do it graphically. We could draw what those two graphs are and solve them. Okay, so compared to what we do in A level, that's actually quite easy. What's tricky is when you have a set of equations where you have three variables. So for example, you might have x plus 2y minus 5z. I said z and then put x, z equals 12. Because there's three unknowns, we need three equations. Negative 4x plus y plus 3z equals negative 2, and a third equation might be 7x minus 3y plus z equals 9. That's quite tricky to solve. Now we can use matrices to solve these, and the first step would be to actually write these set of equations in matrix form. Now the way that we do that, with these equations, we'd form a matrix of the coefficients. So you can see all I'm doing is writing down here the coefficients of x, y, and z. And then next to that, I'll write a matrix that's got x, y, and z. Now you can see that if I were to multiply out this matrix, yeah, I'd get basically 1x plus 2y minus 5z, which is the first row. Second row, negative 4x plus y minus 3z. And the bottom row, 7x minus 3y plus z. You can see it makes the equations on the left, so all we need to do to complete this is to put the solutions here, not the solutions, but what each row makes on the right hand side. So what we can do, we can write those simultaneous equations in matrix form. Now if I call this matrix here matrix A, then if I do the inverse of A to both sides, if I do the inverse of A there and the inverse of A here, then what I'm going to be left with, well, A times this inverse is the identity matrix, so effectively I'm just left with x, y, z, and x, y, z will equal, well, this inverse matrix of A times by 12, negative 2, 9, and then once I've multiplied that out, this will give me the solutions to the simultaneous equations. Now, because this involves finding the inverse of a 3 by 3 matrix, there's quite a few steps involved in that. You are allowed to use a calculator. So what I say is use your calculator, unless you're told otherwise in the question, to find the inverse of that matrix. Yeah. Now to find your inverse of a 3 by 3 matrix, or any matrix actually, first thing you do is you press menu. Then from menu you choose option 4. You see like a block of 4 squares in brackets. Then you want to define your matrix, so you could have it A, B, C, or D. You can define up to 4 matrices. Define your matrix. Let's say you define matrix and you press number 1 for matrix A. You'd have 3 rows and 3 columns. You type your numbers in. At the very end, press equals. After that, we go to option. This after you've typed it in, so OPTN, and we're going to type in matrix calculation number 3. Then we press option again, and we pick our matrix. It'll either be option 3, 4, 5 or 6. Let's say it's matrix A. Press 3. You choose your matrix, and then from there, once you've chosen your matrix, it will say something like this on the screen. Mat A, something like that. You now want to press the x to the -1 button, which is underneath the x squared. And then a little -1, -1 will appear. Then you'll get a matrix. Now sometimes the matrix is full of decimals. If you use the cursor buttons and scroll over to the decimal number, if there's an exact fraction, it will display that down in the bottom right hand corner. Yeah, and they're the numbers we really want to use, these exact fractions, not the decimal equivalents. So this question is saying use an inverse matrix to solve the simultaneous equations. So we're not going to solve the simultaneous equations using our calculator or do it manually. We're going to use matrices. So the first thing we're going to do is to write all the coefficients in a 3 by 3 matrix. So that's -1, 6, -2, 6, -2, -1, -2, -2, 3, 5. Okay, 2 looks a bit like a Z, so I'll just change that a bit. And the same with the other 2 there. Okay, and then we have the letters that we need to solve. In this case, x, y, and z. It's normally x, y, and z. And this is going to be equal to the numbers on the other side. So 21, -16, 24. So the way we're going to solve this, if we say let M equal that matrix there, then using our calculator, we are going to find the inverse. 6, -1. We're not going to do it the other way. We've got all those steps to do. So on our calculators, menu and 4, define a matrix 1, number of rows 3, columns 3, and we'll type in -1, enter, 6, enter, -2, enter, 6, -2 again, -1, -2, 3, 5, and then enter. Okay, I'm going to press the option button, and I'm going to do matrix calculation number 3. Then I'm going to press option again, and I'm going to press number 3 to get matrix A, and then I'm going to press x to the -1 under x squared, and I get the inverse matrix, which is this. Now there are loads of decimals in here, so scroll over the number and write down the fraction equivalents. I've got 1/27, and move across, 4/21, 10/189, 4/27, 1/21, 13/189, -2/27, 1/21, 34/189. So there's our inverse. So if I multiply both sides of the original equation by this inverse and the inverse at the front, what I'll be left with is x, y, z will equal that inverse matrix. Let me just write m to the -1 times by 21, -16, 24. Now I'm going to get the calculator again to do that for me, because there's lots of multiplying out here. So I'm now going to press option again. I'm going to define a new matrix. I'm going to call this matrix B, number 2. This one, the number of rows is going to be 3 and the number of columns is going to be 1. So I enter in 21, negative 16, 24. Okay, press Option and make matrix calculation number 3. Press Option again, and I want to do my matrix A, which is the matrix I've got. Then I'm going to do x to the negative 1 times by, and then I'm going to press Option again and press 4 for matrix B, and I can see the matrix I get is negative 1, 4, 2. Okay, so when we solve those, we get x is negative 1, y is 4, and z is 2. Now sometimes you get questions like this where we need to create our own equations. So a colony of 1,000 mole rats is made up of adult males, adult females, and youngsters. Okay. Originally there were 100 more adult females than adult males. The number of adult males has increased by 2%, females by 3%, youngsters by 4%. The total number of mole rats had decreased by 20. Form and solve a matrix equation to find out how many mole rats there were in the original colony. So I'm going to call the adult males, I'm going to call X. The adult females, I'm going to call Y. And the youngsters, do you actually call mole rat youngsters? Well, here we go. I'm going to call them Z. Now, what equation can I write down? Now, if I look at the start, 1,000 mole rats made up the colony. So, the adults, the females, and the youngsters is 1,000. So that's equation number 1. So originally there were 100 more adult females than males. Okay, so the number of males plus 100, is that right? So there are 100 more adult females. Yeah, so the number of males plus 100 equals the number of females. So I might rewrite that as x minus y plus 0z, or Oz, equals negative 100. Yeah, if I just move stuff around. And then it says that, what else have I got here? I've got something about after 1 year, so the adult males had increased by 2%, so that's 1.02 x. The number of females had increased by 3%, so that's 1.03 y. So this x, y, and z stands for the original number of these mole rats. And it says the youngsters had decreased by 4%. So we have now got 96% of the youngsters. And the total number of mole rats had decreased by 20. So it's gone down from 1,000 to 980. Right, so I have my 3 equations here. And what I'm going to do is now write these equations in matrix form. So that's going to be, so remember I start with the coefficients of each equation. So the first equation is 1, 1, 1. The second equation is 1, negative 1, 0. And the third equation is 1.02, 1.03, 0.96. And that is going to get times by x, y, z, like that. So there's the left hand side of the equation, and the right hand side of the equation is going to have these numbers: 1,000, negative 100, negative 100, and 980. So the first thing we're going to do is we're going to find the inverse of this matrix using our calculator. And let me call this matrix here A. Yeah, call that A. So I'm actually going to be working out A inverse here. Well, I'm not going to be working out, the calculator's going to be working out. So we're going to, if we're still in matrix menu, which is menu 4, and we're going to define a matrix. I'm going to define matrix A, which is 3 by 3, and I'll type in 1, 1, 1, 1, negative 1, 0. So even though it's 0, still type it in. 1.02, 1.03, 0.96. Right, okay. Then I press Option, Matrix Calculation, press Option again, and number 3 for matrix A, and then a button underneath x squared, x to the minus 1 will give me the inverse. Okay, and this is one of these ones where not nice numbers, so we just go over each bit, and we're going to write down what the numbers are, the fractions. So the first one is negative 96 over 13. Moving across, 7 over 13. 100 over 13. Now if they're all going to be over 13, I suppose we could put 13 at the front. So negative 96 over 13 down here. Negative 6 over 13. 100 over 13. Down to the bottom row. 205 over 13. Negative 1 over 13. And negative 200 over 13. So that's what I get from my calculator. Now I'm going to do this inverse matrix, so this to both sides. Okay, so let's just write that down. So I'm going to do A inverse here, A inverse here. So what I'll be left with is XYZ, XYZ is going to be equal to this inverse matrix multiplied by 1000, negative 100, 980. So we're going to let the calculator do the work for us. So I'm going to press Option and define a new matrix. I'm going to call this matrix B. And this matrix is going to have 3 rows and 1 column. So I just type in 1000, negative 100, 980. Okay, press Option, number 3 for matrix calculation. Press Option again. And I want to do matrix A 3 times by, or actually the inverse of matrix A. So I need to press x to the minus 1 times by, press Option, and number 4, matrix B. And what I get is 100, 200, 700. That looks nice, doesn't it? So this will be my answer. This is the number of adult males, adult females, and the youngsters. Now, you may be wondering what all these diagrams are here. When we solve simultaneous equations where we've got 3 unknowns and we have an equation of this form, ax plus by plus cz equals d, where a, b, c, and d are can be any real number, so we write it like that. Okay, so they could be whole numbers, they could be fractions, decimals, they could be positive, negative. When we solve equations like that, these equations give a plane. They don't give a line, they give a plane. So basically we're drawing something in 3 dimensions. So this is the equation of a plane, and a plane is a flat area. Now all of these little diagrams are showing planes, 3 different planes. So they are 3 different equations. So each one of these planes represents one of these equations, ax plus by plus cz is d equals d. So we've got three different equations. Now these planes, these big flat areas, sometimes they meet, sometimes they cross, sometimes they don't. Sometimes they run parallel to each other, sometimes just two of the planes cross, all three of the planes cross, and that all depends on the number of solutions. So each one of these diagrams represents three sets of simultaneous equations in x, y, and z, and it's showing the possible different combinations you could have with the planes or the equations, and what they can look like. So the very first one, which is this one here, okay, what you'll notice is that all the planes meet at a single point. They meet at a single point, and that single point is here. Now what does that tell us? That means all three equations solve with one solution, like the last two that we did. The last two equations that we did had one set of solutions. X was equal to something, y was equal to something, z was equal to something. So if we were to draw out the planes represented by the equations in the last two examples, they would all cross and meet at one point. They may not all be perpendicular like they are in this diagram, but they would all cross at one point. Now, whenever the equations can be solved so that there is a solution, all three of them have a solution, we say that they are consistent. Okay, we'll talk a bit more about this in a moment. In this case, these consistent equations have one solution. And one way that we can determine whether a set of equations has one solution is by looking at the determinant. And if the determinant is not equal to 0, all of the equations will solve with one solution. They will meet at a point. So here we can determine if we're going to get this because the determinant will be non-zero, which means that the matrix is non-singular. So anytime we work out the determinant is non-zero, we know that all the planes meet at a point. In the second one, over here, this one here, you'll see that all three planes don't meet at a point. They do meet, but they meet at a line. Let's take that shade off because they all look the same color. There we go. And in this case, the determinant would actually be 0. And in all the others, actually, the determinant is 0. So there isn't a unique solution, but there are a set of solutions here along this line here. Yeah? There are an infinite number of solutions here. Anywhere on this line is a solution to all three equations. So for example, if we had something like, we ended up trying to solve three equations and we ended up with something like x plus y equals 5. That's the equation we ended up with at the end. Well, that has infinitely many solutions. You can have any values for x and y, and that will balance. So we will end up sometimes with that type of equation. Now, when the planes cross like that, it's called a sheaf. And we need to know that. We need to know that when we get an infinite number of solutions, we get a sheaf. Now, just like where they cross at a point, we say that these equations are consistent because yes, we can solve all three, but when we solve all three, there are an infinite number of solutions. Okay, so far we've had things that meet at a point, which are consistent, have one solution, and the determinant isn't equal to 0, it's non-singular. Now we've had something called a sheaf, where there's an infinite number of solutions. It's still consistent. And here this matrix would be singular. Okay, now the third one, this is called a prism. When the planes cross like this. Now you can see that pairs of planes cross, but all three planes do not cross at a single line or a single point. What that means is each pair of equations has a solution, but there is no solution to all three. Now, when there's no solution to all three equations, we say that it's inconsistent. There's no solution to all three equations, only to pairs of equations. So there's like a solution here for this pair. There's a solution here for this pair, and there's another solution hiding behind the back for that pair. And again with this, the determinant is 0. Yeah, the only one where it's non-zero is where they meet at a single point. So we have a point, a sheaf, a prism, and then we have some more at the bottom here. We don't need to know the names of these ones. This is just to show you the other things that we can have. Well, actually, we do need to know one more. This one here. This is consistent, yeah, because all three planes are basically all in the same place, and this has infinitely many solutions. So this is consistent as well. Again, the determinant would be equal to 0. And this is where it's not really a name here, but you would say something about where all equations in the same plane. That would normally happen if the equations were all multiples of each other. Okay, and then we have one here which is inconsistent, just like the prism. So this one here at the bottom, where you've got like this H shape and these three planes stacked one in front of the other, is inconsistent. Just like the prism, there are no solutions. So you can see on the first diagram, the H-shaped one here, while the blue and the green have infinite solutions. The red and the green have infinite solutions, but there's no solutions for all three. And these planes stacked one in front of the other, there are no solutions for any of them. So let's recap what we've done so far. So we can either have, let's check the determinant. So the determinant, let's say the determinant is not equal to 0. Well, in that case, all the equations would meet at a point, and because there's solutions or a solution for all three, so point, let's just put one solution, which means it's consistent. Okay. Anytime there's a solution or solutions for all three, it's consistent, right? So let's move over here where the determinant will equal 0. So when the determinant equals 0, you can have different situations. So you can have infinite solutions, or you can have no solutions. Right. When I have infinite solutions, I'm either going to have a sheaf, or all the equations are going to be in the same plane. The sheaf are all in the same plane, so we say that they are consistent. Okay, now when there are no solutions, we will either have a prism, or we will have, I don't know what to call these ones, we'll have either this one or this one, like the one stacked in front of each other, the one that looks like a H shape, there. Then those ones have no solutions, and we say that they are inconsistent. So as long as there is some sort of solution or solutions, it's consistent. So a single solution or many solutions, consistent. If there are no solutions for all three equations, they are inconsistent. And if there's one solution, it will meet at a point. If there are infinite solutions, it will be a sheaf. If there are no solutions to all three, but to pairs, then it will be a prism. And we need to describe what type of solution we get, and also the shapes that the planes will make, either a point, a sheaf, or a prism. Okay, so in this example, we have a system of equations. Here, for each of the values of k, determine whether the system of equation is consistent. That means either that there's either one solution or many solutions. That's what we need to decide. And inconsistent is just going to mean no solutions. If the system is consistent, determine whether there is a unique solution, which means they meet at a point, or an infinite number of a solution, or infinity of solutions, which means that we're going to get a sheaf if that's the case. Okay, so let's start with A. So what we're going to do, we start with the determinant, because the determinant will determine whether there is one solution or whether it's going to be many or no solutions. So we're going to save time, and we're going to use our calculators to work out the determinant. So in the first one, we're going to have k is going to be 0. So we want to work out the determinant of the matrix. So maybe the first thing I'll do is to write out what this would look like. So the coefficients here, 3, negative k, just makes it easier for each one. Negative 6, k, 3, 3, negative 3, negative 1, 3. And that's going to be x, y, z equal to k to negative 2. It just makes it easier to write things out. So in the first one, k is 0, so I'll have 3, 0, negative 6, 0, 3, 3, negative 3, negative 1, 3. And I want to find the determinant of that, so I'll just write this. So that I can do on my calculator. Okay, now I've defined this matrix on my calculator, and now what I want to do is to find the inverse of that matrix. So if I press option, and I think do matrix calculation, and then option again, if I scroll down to the second page, then it says determinant. So I press number 2, and determinant, press option, number 3 for matrix A, that's what I've defined, and I get a determinant of negative 18. Right, so what this tells me, negative 18, that because this is non-zero, it's non-singular, it means that there is a unique solution. So unique solution, we need to describe this what we call geometrically. So that means we need to describe how the planes meet. So unique solution, planes meet at a single point. Okay, so we need to describe it in that way. Right, part B. So now this time k is 1. So I'll have 3, negative 1, negative 6, 1, 3, 3, negative 3, negative 1, 3. We're going to work out the determinant of this one. Right, I've done that, and this one gives me a determinant of 0. Now, all this tells me is that there isn't a unique solution, but there could be infinitely many solutions, or there could be no solutions. And that's what I need to do now. So I actually need to solve these simultaneously and see what I get. So let me write out what these equations are going to be. So that would be 3x minus y minus 6 equals 0. And then x plus 3y plus 3z, no, sorry, not equal to 0, equal to k. So it's going to be equal to 1, k is 1. Sorry about that, that should be 1, 2, and then the last equation is going to be negative 3x minus y plus 3z equals negative 2. Now what I'm going to do is I'm going to label these equations 1, 2 and 3. And I'm really looking for equations that have got the same coefficient in, so I can put them together now. This and this one have a negative y, so the same coefficient there. I've just noticed that I've missed out a z on the first equation, so there we go. So I'm going to do equation number 1 minus equation number 3. Yep, going to be same sign, subtract, so that's going to be 3x minus y minus 6z equals 1 minus negative 3x minus y plus 3z equals to negative 2. Right, so let's do that. So that will be basically 3 plus 3 is 6x, then the y will disappear, then I will have minus 9z equals to 3. So let me simplify that, divide everything by 3, and I get 2x minus 3z equals 3. So that's my first equation. Now I want to do the same thing with two different equations so that I end up with another equation with x and z. Now you can pick any pair of equations to start with, but you want to eliminate the same letter using different pairs of equations. Now this time, let me have a look. Oh, I've accidentally deleted the coefficient or the y term. That was negative y there. So this time I'm going to choose equation 1 and 3 again. I'm going to do, no, so 1 and 2. I'm going to do equation 2, take away, no, add 3 lots of equation 1. Now if I do that, I will get the y term to disappear again, which is what I want. I want another equation just with x and z, but using two different equations. So let's write these down. So equation 2, x plus 3y plus 3z equals 2. And then 3 times equation 1, so that's going to be 9x minus 3y minus 18z equals 3. Right, so this time I'm going to add them. So I end up with 10x, then the y's will disappear, and then I will have 3 minus 18, which is negative 15z, equals 5. So I can simplify that, divide everything by 5, and I'll get 2x minus 3z equals 1. And I've just realized actually, didn't I say I was going to divide the last equation by 1? So that should be 1 as well. Now what do we get here? Two sets of equations with exactly, well, they're both exactly the same. So we've got 2x minus 3z equals 1 from one pair of equations. We get 2x minus 3z from using two different equations. So what does that mean? Actually, there's an infinite number of solutions, because actually solving one equation is solving the other. I can't now eliminate x or z. So here there's an infinite number of solutions, infinite solutions. So there is a solution to all three equations, but this time, because there's an infinite number of solutions to all three equations, we have a sheaf. Okay, so there is an infinite number of solutions. Now we also need to say that the equations are consistent, because there's all three can be solved, not just pairs of them. So it's an infinite number of solutions. I suppose I should have said first, the equations are consistent, running out of space. There's an infinite number of solutions, therefore the planes meet as on in a sheaf. Yeah, because the equations that we had left, there's an infinite number of solutions. Right, let's have a go at the last one now. So in this last one, k is going to be -6. So let's just reuse this one here for c. So c, so if k is -6, we end up with 3, -6, -6, -6, 3, 3, -3, -1, 3. Okay, let's set this up on our calculator and work out the determinant. Right, k is -6, isn't it? So actually that means that that is +6. Yep, that's the only thing that changes. Right, this one also has a determinant of 0. So what we need to do is to solve simultaneously so that we can determine whether it's consistent or inconsistent, and whether we have a sheaf or a prism. Right, so we're going to do the same thing as we did last time, and that is get pairs of equations where we can just have two letters in the equation, make it look like a GCSE, simultaneous equations, and then see if we can solve those. So first of all, let's write down what the equations are. So that'll be 3x plus 6y minus 6z equals k, so that's going to be -6. Second equation, -6x plus 3y plus 3z equals 2. And last one, -3x minus y plus 3z equals -2. So let's number these 1, 2, and 3 so we don't get confused, and make sure that we involve all three equations. So let's look for coefficients which are the same. Right, I see that 2 and 3 have the same z coefficient, so I could do equation 2 minus 3 and end up with equation just with x and y. So let's do that. So if I put 2 minus 3, that will be -6x plus 3y plus 3z equals 2, and then -3x minus y plus 3z equals -2. So I need to subtract to eliminate the z. Just saves me having to multiply. So I've got -6 plus 3, which is -3x. Then I will have 3 plus y, so that makes 4y. The z's will disappear, and that will equal 2 plus 2, which is 4. Okay, can't simplify that, so that's going to be my first equation. Now, to form my next equation, I mustn't use 2 and 3 again. I've got to involve equation number 1. Now if I use number 1, again I want to get rid of z. So if I did equation number 1 plus 2 times equation number 2, that would work. So let's write that down. So I'm now going to do equation number 1 minus 2 times number 2. So that will be 3x plus 6y minus 6z equals negative 6. And then 2 times the second one, negative 12x plus 6y plus 6z equals 4. So this time I'm going to subtract, no, add, as I said. So then I have 3 minus 12, so that we're negative 9x. Now this time the y, well no, it doesn't disappear, plus 12y equals negative 6 plus 4 is going to be negative 2. Let's simplify that. Now I can't simplify it. So now what I'm going to try and do is attempt to solve these two equations. Now last time I didn't need to, I ended up with the same equation. On the last one, even if I ended up with multiples, you simplify, you end up with the same equation, infinite solutions. Now can these be solved? Let's have a look. So if I take the top one, this minus 9x plus 12y equals negative 2. Let's take this equation and let's times it by 3 and see what we get. So we get negative 9x plus 12y equals 12. That doesn't seem right, does it? What I've got is exactly the same equation, but with two different numbers here. That's impossible. That cannot happen. So this means that actually I found two that don't solve. There may be two that do solve, but here there are no solutions. It's inconsistent, and whenever there's no solutions and it's inconsistent, then what we have is a prism. Our answer is only going to ever be a point, a sheaf, or a prism. So here, in this case, because there's no solutions, because of what's going on here, we say it's inconsistent, because there isn't a solution for all three, or solutions for all three, all inconsistent. And if it's inconsistent, we don't have an infinity of solutions for all three equations, maybe for pairs, but the pair we picked, there was no solution. So we'll say that the planes meet at or as a prism. The planes meet as a prism. Right, you should now be able to do exercise 6F on pages 120 to 121. So let's just recap what we've learnt about these simultaneous equations. So we can form our simultaneous equations into matrices and use the inverse matrix to solve. I think that's straightforward. You can always go back and look over the examples. It's then when we need to describe the solution, what happens with the planes. Well, first of all, we want to work out the determinant. We want to work out the determinant. Right, if the determinant is not equal to 0, what does that mean about our matrix that we're using to solve the equations? Well, it's non-singular. And if it's non-singular, it means that the planes meet at a point, and we have a unique solution. We have a unique solution. So x equals something, y equals something. z equals something, just a single solution. Okay, if the determinant does equal 0, right, there are two possible choices that we're concerned about. The first one is that the planes meet at a sheaf, and they will meet at a sheaf when we have infinite solutions or an infinity of solutions. Okay, and that would normally happen when you go about solving your simultaneous equations. You might end up with something like 4x plus 3y equals 7, and then you end up with 12x plus 9y equals 21. So these are like multiples of each other, or you might end up with the same equation. So this is just an example of what you might get. And even if you get an infinity of solutions, we say it is consistent. The system of equations is consistent in the same way that with a single solution, the system of equations is consistent. So as long as there are solutions, whether it's a single one or many, they're consistent. The last thing we're interested in is when the planes meet at a prism. Now, here, only pairs of equations solve with infinite solutions. Okay, only pairs of equations solve with infinite solutions, not all three. So there is no solution for all three, in which case this is inconsistent. So we're not worried about the planes that meet in a H shape, or the planes which sort of are all parallel to one another. We're only interested in describing whether it's a point, a sheaf, or a prism.